Hey everyone, Natasha here. Let's get started with our first lab. We're going to be going through partial and semi-partial correlations together. So let's get started. All right, so I hope you went ahead and you downloaded that zip file that is named partial and semi-partial correlations. And that's all that I have open on my desktop at the moment. And so what I need you all to do here is simply select partial and semi-partial correlations HTML file. When you do that in a new window, our lab for today will go ahead and it will populate on your screen. And then from there, if you could please open RStudio because we are going to be starting a new project. All right. And so what I need to do is I need to go to File, New Project. Then I'm going to go ahead and select New Directory. From New Directory, I'm going to go ahead and select New Project. And then I want this new project to be in a folder that is specifically on my desktop. So what I need to do is I need to go to that second option there and select Browse. And I just want to triple check to make sure that the correct folder is where everything's going to be populated. My new project is going to be. So absolutely, it is right now in my UCSB folder. So I'm going to go ahead and open that UCSB folder one more time. This is where my project is going to be housed. It's a subdirectory of my project. And so I need to create a new project name here. And so my new project name is simply going to be partial and semi-partial correlations. I want to go ahead and I want to start in a new session. This will literally create a new RStudio session. All right. Now, in this new RStudio session, I want you all to recognize that I don't have an R script open right now. I don't have an R markdown that I can go ahead and edit or a QMD file, whichever one of those that you work with. In order to do that, what I want to go ahead and do is that first, I'm going to use this little toggle button that is on the right-hand side here. It kind of looks like they're two pieces or two pieces of paper or two screens kind of sitting on top of each other. I'm going to pop that open. And so that will give me a new R script to work with or to edit in. But rather, I want to be working with a either an RMD file or a QMD file, whichever one that you actually prefer. And so to do that, I'm going to go to the very top bar on my computer here that is related to RStudio. I'm going to go ahead and select File on that very left-hand side. A drop-down menu will fall. I'm going to go ahead and select a new file that I want housed in my new project. And so I'm going to go ahead and select an R Markdown file. And so a new window will populate. In this new window, it's going to ask you to give your new R Markdown a title. So in this case, I'm going to title my new R Markdown as partial and semi-partial correlations. And so my name is there. I'm just going to go ahead and edit that. You can if you'd like to, along with the date. And then also selected is the current date when rendering document. That means every single time that you knit this file, that's the date that's going to be generated when rendering the document. And then we also have selected HTML as the output. You can go ahead and select Word if you have to go ahead and turn it in as a Word document also. I'm just going to go for the sake of this video as HTML and select OK. All right, so there is my new RMD file that has then been generated in my new project. The thing that I notice here is that my new RMD file is not saved yet. I know this because it's still called untitled, and in my partial and semi-partial correlation project folder, I don't see that RMD file saved. So I'm going to go ahead and select file in that upper bar on the left-hand side. Then I'm going to go ahead and hit save as I scroll down here. And then I'm going to title this partial and semi-partial correlation, or you can even put down core for short. And I'm going to go ahead and hit save. And I know that this RMD file is now saved and it's housed within my project by looking at that fourth quadrant here, that fourth panel, and partial and semi-partial correlation RMD file is now visible in that fourth panel or that fourth quadrant. And in the second, you can see that I finally in that tab have a name and that it has replaced the untitled previous name. All right. And then from there, now I want to go ahead and I want to delete everything that was generated or populated by default, starting with line 8 all the way through 31. And I'm just simply going to hit delete after I have highlighted everything. So delete. Perfect. Now, I want you guys to all go ahead and split your screen where your RMD file is going to be on one side of the screen and your HTML on the other side of the screen. So that way we can go ahead and follow along. All right, so let's get into partial and semi-partial correlations. Using some simulated data that is really inspired by a study that focused on teacher burnout. And so we are going to be using these correlation techniques to investigate the relationship between the number of teacher callouts related to their class sizes that they actually end up instructing in. And then we're also going to be considering in the presence of or controlling for the number of years that these teachers have had within their classrooms. And so actually, prior to jumping into that code, I'm going to be briefly reviewing some techniques that we can use to handle data that had been previously spoken about or lectured about, and then also how to go ahead and identify outliers using plots here. And so what we all first need to do is we need to download, or rather start with our packages. And so I need you all to go ahead and create a new R code chunk. And how you can go ahead and do this are several ways. So I prefer the keyboard shortcut Option Command I for my Mac users, Option Command I. For my Windows users, that is going to be Control Alt I. Control Alt I. All right. Now, what if you could all go ahead and please use the copy code option here. And you can see the copy code option with that little clipboard that is located on the right-hand side of all my code that you will need for this section. So go ahead and use that. So copy, I went ahead and I copied all of these packages that I have called in using the library function. And so now all you have to do is just paste. And you can do that two ways. You can do that through the edit option in the bar up above the RStudio bar. And when you go ahead and select edit, a drop down menu will fall and you can go ahead and select paste. or you can go ahead and if you are a keyboard shortcut user, you can use Command V there. Or for Windows users, you can go ahead and select your own keyboard shortcut. And so in my new uh, R code chunk, I have all of my packages listed. Okay. And so then you can go ahead and run all of these packages if you have them. If you do not have all these R code packages, you are going to have to install them. And so in order to install these packages onto your own computer here, you're going to want to go ahead and type out install packages, and then in quotes here, for instance, if you don't have the ggplot, you can go ahead and type out ggplot2 and then run that line of code if you need to. I typically do all of these types of installations in my console, and that is the third panel or the third quadrant here at the bottom. And so I would go ahead and just type out installed packages and then ggplots. And I would do this for every package one more time that you do not have. And so these are all of the packages that we're going to be using. I leave you here with some notes on how and why I go ahead and I include these packages. And so you can go ahead and run those all. I'm going to run them here. All right. And no problems for me because I've already downloaded all of these packages. So please just make sure that you have all of these packages downloaded so you can go ahead and use them for this section. All right. And so I'm going to then start my new R code chunk by one more time, Option Command I on a Mac, or for my Windows users, one more time, that is Control Alt I. Control Alt I. It's just super simple, super easy. All right. So let's go ahead and first define what partial correlations are. When it comes down to partial correlations, the whole point is that we want to go ahead and evaluate the relationship between two continuous variables after accounting for the influence of a third continuous variable. Sometimes this is referred as an extraneous factor. It may be a confounding factor, but it is a third factor that plays some sort of role or some sort of influence in our relationship that we're truly interested in evaluating. All right. And so in the case of our example here, we are going to control for the number of years of teacher experience, a confounding variable while evaluating the relationship between teacher callouts and class sizes that they actually work in. And so I'm going to go ahead and get into how these relationships work. Okay. So, first, I do want you to know that we have some hypotheses that we can go ahead and report when we are using these types of techniques. And in this case, we have a null that suggests that there is no relationship between our predictor variable and our outcome variable after controlling for some sort of extraneous variable, and that is that the relationship is equal to 0. Okay. In the context of our study here that we are interested in, the relationship between the number of teacher callouts and total number of students are not related after considering the influence of the number of years of teacher experience. And so the alternative would be that there is a relationship, that the relationship or the correlation, the partial or semi-partial correlation is not equal to 0, but the relationship between the number of teacher callouts and the total number of students are related after considering the influence of the total number of years teachers have spent teaching. Okay. I do want you to know that there are some assumptions that need to be evaluated prior to using or employing this type of technique, which you all have seen and heard before. And we're actually not going to be generating any type of code for these to evaluate these assumptions just for time's sake, but I'm sure that you can find them elsewhere. All right. So when it comes down to linearity, just to remind you, it's that the relationship between the pairs of variables goes in one direction, that it's monotonous, right? And that there is the absence of a curvilinear relationship. And we can go ahead and use scatter plots to evaluate this assumption of linearity. And then when it comes down to independence, we are suggesting or that we know that the observations or the responses from our observations are independent from one another. And that is saying that our responses, our values are not relying on one another, that they don't come from repeated measures or continuous exposure to the same thing over and over. And so this is also, you can think about it as time series or maybe even an experiment with repeated exposure itself. And then to go ahead and make sure that this is not the case, you just really have to know the methodology used to collect the data and to conduct the study. And then when it comes down to normality, this is just saying that the distribution of the observations or of those scores are follow a bell curve or are normally distributed. And so you can go ahead and use histograms or QQ plots to evaluate this normality assumption. Last and definitely not the least is no outliers should be present, although it's not um, an absolute assumption. That I do want you to know that any type of extreme responses can influence your correlation. And so there are different ways that you can go ahead and handle these outliers. Some folks go on and end up removing them and comparing analyses from when those outliers are removed versus when they are not removed. And the best way that we can go ahead and really identify them early on is by using plots or other types of functions that can help us identify those outliers. I do want to then jump into how we are going to actually run a partial or semi-partial correlation. This is only one way to do this. There are simpler ways, but I really want you all to understand what is happening with semi-partial correlations. And in order to do this, we're going to be using a linear regression model residuals. And so, and so a partial correlation can be obtained by correlating the residuals of main variable and all other main variables after controlling for that extraneous or that confounding variable, that variable that's playing an extra role that you just don't want it to play. And so I do have a couple of terms in here that I just want to remind you about. For instance, residuals. Residuals are simply whatever variance that is remaining or unexplained after predicting an outcome from some variable. It's whatever is left over. It is the difference between, I'm going to use my little pen here. It is the difference between our regression line and whatever given point. So for instance, I have this point way up here up that top, I put a red dot by it, and all of this distance, right? Let's just say hypothetically, all of this distance between the regression line and that one data point, well, this could all be considered residual. Everything that is not yet have been explained within call out, right? And so then same thing. Let me go ahead and clear all my drawings real quick. And I'm going to stop that pen. Same thing here down below is that we are going to be pulling out the residual, whatever is left in that outcome that is yet to be explained by another variable here. In this case, we are going to have the relationship between callouts and experience, and then class size and experience, and whatever is left over is what we are going to be correlating. Okay, so whatever is left over is what we are going to be correlating after we have already taken into consideration what has been explained by experience. Okay, so we're going to be relating these two parts. We're going to be getting a correlation here, and that's supposed to be a row. All right, so let me go ahead and delete all that. Okay. And that is really what a partial correlation is. One more time, we are taking out the influence of that third variable, of that third confounding variable from both the call out and from the class size, suggesting that these two main variables that we are highly interested in evaluating together, that they're influenced by this one confounding variable. In this case, it's going to be experience. So one more time, we are removing experience from callouts and from class size because they play some because experience plays some sort of role in these two variables that we are wanting to relate to one another. Okay. All right, so before we actually get into our example, we need to go ahead and make sure that the data that we are going to be using today is in our working directory. So that way we can go ahead and easily call it. All right, and so I have several ways that I like to do this, but I'm going to show you one of my favorite ways that I typically rely on. And so first I'm going to minimize my two screens here. I can populate those right after again, or I can pull them back up right after again. And so as you can see, my zip file is here still on my screen, and I am going to literally drag and drop those two files into my working directory that I had set up. And I know my working directory is on my desktop in my UCSB folder, and I had named that new project partial and semi-partial correlations, and it is there. And so all I'm going to be doing is dragging and dropping. One more time, I'm just going to drag and drop those. All right, so let's go ahead and let's wrangle this data. Well, let's clean up this data. We are going to make sure that every column is a variable and that every row is an observation that is nice and clean and tidy. What does that mean? That we also have dealt with invalid values, missing data, or any type of format issues that can mess up a really clean data set. So let's get started by generating a new R code chunk, Option Command I for my Mac users, Option Command I, or for my Windows users, that's Control Alt I. And so let's go ahead and describe this data. Specifically, we're going to be focusing on the teacher data that has missingness in it. And I have titled that uppercase T underscore DF underscore missing. And I'm just going to use that clipboard function there that I have provided for you. And I'm just going to paste it into my R code chunk, and I'm going to run that. And so you will then get some of the descriptive statistics that we normally want and see. And one of the first things that I am noticing is that, let's see here, is that For instance, in my experience variable, there are 4,339 participants that reported or had their number of years of experience reported in comparison to callouts, class size. I also noticed something else. I noticed that there is a 1 for that first column, or that for that first variable. That is very strange. One more time. And this is what I'm talking about when I'm talking about issues with format. We don't want that 1 to be there. What does that even mean? I have no one clue. We can go ahead and then take a look at our data itself and figure out, well, what exactly is it? So this is another thing that would be brought to my attention. Okay. All right. That's just one way to go ahead and to look at your data prior to getting into analyses. And the first thing I'm going to do is fix that first column, because that column is actually supposed to be participant IDs, just 1, 2, 3, 4, 5. Okay. And so how I can go ahead and do this, folks often come into office hours and ask me, like, how do I recode or how do I rename a variable? And I'm going to show you how to do that using the rename function. And so I'm going to go ahead and use a new R code chunk for this, just because that's how I prefer to run my data, or to run my analyses here. And you can simply go ahead and, one more time, either you can copy this clipboard and paste it. One more time, you can copy the code using the clipboard and paste it, or you can type it out yourself, where you first would type out the name of the data set that we're using, and that in this case is T_DF_missing with a pipe. This pipe is simply suggesting that we want the next function that follows this pipe to be implemented on the following data set. In this case, the TF_DF missing. Okay. And that's all the pipe is doing. It's just a shortcut for us. And so by us then assigning this new renaming of column 1 to ID, we can go ahead and then write over that first column name. So I want to show you what happens. All right, so I went ahead and I highlighted that code chunk, and I went ahead and I hit Command return. And so I can go ahead and type out now in my console names, and that'll pop up automatically. And I'm going to type out the data frame, and that'll automatically generate. And I can see that my first column is no longer a 1, but rather listed or named as ID. Great. So I have renamed a column. That is one tool that you will always have in your back pocket or in your chest of tools. Okay. So the rename function, how you can rename a column. Next, we are going to get into visualizing. I love to visualize my data before actually getting into any type of analyses. And so here we're going to use box plots rather to identify any outliers. And so you can simply, one more time, use the paste clipboard function that I have provided you within this HTML to generate that. You could also type it out yourself. One more time, create a new R code chunk. I'm going to hit Option Command I, and I'm going to first type out my my data frame name, and then it's automatically going to generate from the global environment. And then I'm going to type out a pipe, because that is a shortcut that I love using. And my shortcut for using a pipe is Shift Command M, Shift Command M. Okay. And then I'm going to use the ggplot function within the ggplot2 package. And I'm going to go ahead and select the ggplot function that is generated in R automatically by hitting return or enter. Two parentheses will automatically generate. Within these two parentheses, it will always start off with AES. What does AES stand for? Aesthetic mapping. You always have to start off a ggplot with aesthetic mapping, all right? Because this is simply setting up the plot itself with an X and a Y axis. No data points are going to be projected onto this X and Y yet. Okay, so X is going to be empty in this case. So X equals and then empty because I want to generate a box plot. Okay, and so then I'm going to go ahead and type out Y equals, and then I'm going to type out call out and it'll automatically generate. This is one way where I figure out if I am actually calling in the right variable, if it automatically is being generated for me. Okay. And then from there, I'm going to go ahead and uh, uh, add a plus symbol to the end of this argument here by selecting or hitting Shift and then the plus symbol on my keyboard. I like to hit return because I love every argument on their own line. And so now, in order for me to actually get a box plot on my X and Y axis, I need to go ahead and type out geom underscore box plot. And that'll automatically populate. And all you have to do is hit return. And then when that happens, two parentheses will be generated. In this case, I'm not going to be putting any type of specifications, but rather I'm going to be adding another plus symbol. Okay. And then from there, I'm going to go ahead and type out theme underscore minimal. And the reason why I'm doing this is because I want to make sure that certain type of characteristics are implemented on my box plot. And that's just simply making the box plot visualization as simple as possible. And so there are other types of themes that you can go ahead and use, but this is my theme that I love using across most of my plots here. And all I have to do is simply run this line of code. You can, rather, lines of code. You can simply either highlight by dragging your cursor across these four different lines here and then running, or you can go ahead and just highlight all of it, command return or command enter, and then you will get, you should go ahead and get your box plot here where you can see, for instance, I have call out visualized here. A couple things that I am noticing is that we have extreme values beyond the quartiles here. And so then I can start thinking about, okay, so maybe I have outliers in my data. Okay. And so I'm going to do exactly the same thing. I want to visualize years of experience and class size. So I'm simply going to copy those lines of code that I have already given to you, and that using the clipboard on the HTML file. And then I'm going to go ahead and start a new R code chunk in my R Markdown by hitting Option Command I and pasting it. Okay, and so one more time, this is for visualizing our class size this time. I'm going to run the data simply by using that play button here. And one more time, I'm just trying to show you that there are multiple ways of doing things in RStudio rather. Okay. And then the same thing here in my HTML file, I'm going to copy my lines of code in my HTML file for generating a box plot for experience. going back to my RMD file, hitting Option Command I to generating that R code chunk, pasting that R code chunk, and then I'm going to run it whichever way that you prefer. Command return for me, because I just prefer that. I really love how ggplot does the following. It provides a warning. It notes that it had to remove 228 rows containing no values, containing no values. And it does this for a reason. It's because it can't generate that code. Sorry, it can't generate those points. So it has to remove those observations. And so here, one more time in my box plots, I'm noticing that there are extreme values, those values that are beyond my median, beyond my upper and lower quartiles here, my third quartile there. And so then I can go ahead and then try to figure out if they're truly outliers in my data set here by using a different code. So there's the visualization, but now I want the code to actually be able to identify which values are considered outliers and the case number that is associated with those values. And how I'd like to do this is go ahead and call in or actually produce a new R code chunk for yourself. Option Command I for my Mac users, or Alt Control I for my Windows users. I promise I'll get that one sooner or later. All right. And so I am going to be using the identify outliers function that is actually in the R statics package. It is one of my favorites, and I use this for one more time, identifying outliers. So I'm just going to type out a note for myself. I'm going to say identifying outliers using R statics. Okay. And so I am going to first, oh, I'm first going to go ahead and type out the name of my data frame here, and it's going to be T underscore DF missing, and you can see it automatically populates when I start typing away. So I'm just going to hit return, and then I'm going to do Shift Command M to generate my pipe one more time. It's just a shortcut saying that in this following data set, or this data frame, I want to conduct the following functions. And in this case, I want to go ahead and use the function identify and then underscore outliers. And you can see it automatically generates and populates. I'm going to go ahead and select that identify underscore outliers and hit return. And then I want to go ahead and find those outliers in my data set here. I'm going to put in those parentheses call out. I am going to actually be, let's see, assigning this to another data frame or another object. So I'm going to use option and then dash, option dash, option dash, and my assignment will automatically generate. So my assignment there will automatically generate, and my object name is going to be outliers, or outliers call out, I think is what I have in the HTML. So I'm going to go ahead and run this. All right, and I'm going to just take a peek at this. Once I run that, you're going to see a new object jump into your environment. That's that first quadrant, that first panel, and I'm just going to go ahead and take a peek at it by selecting it. And so what you are looking at now is kind of like this object or this data frame. It's not a data frame exactly, but it's an object, and it has, for instance, the ID values along with call out, class size, experience, and several other new columns that we didn't have before. And that is whether the values or the ID is considered an outlier and true, and whether it is extreme or not. And in this case, we're thinking about things such as leverage, which you all have heard before. right? And so then you can go ahead and see that, yes, we may have an outlier here with an extreme value for call out, class size, and experience. And it is happening for my 28 cases that are listed here. And these are their IDs. I do want you to know that if you do not have an ID column, that uh, this particular function will not give you that ID, but rather it will just give you the values. And so this is why I have an ID column in this example, and I think it's always super useful to have one just in general. Okay, so these are the outliers that I have here. No, I'm not going to be doing anything with my outliers just for the sake of time and for the sake of this recording. All right. So I'm going to go back to my RMD file. And so if you would like to, you can actually print out the IDs that are considered to be outliers by typing out print. When you start typing out print, you will see a drop down automatically generated. Go ahead and hit return or enter. Two open parentheses will be generated. In those open parentheses, please type out the object. So outliers is the object underscore call out that is in our environment. And you want to go ahead and print out those IDs that are suggested to be outliers. And so then I'm going to then hit shift and the dollar sign, and that should be number 4. And then I'm just going to go ahead and select ID. And so when I go ahead and do that and I print that out, or I go ahead and hit command return or run, I get all of those IDs that are considered outliers in that object. All right, moving on. All right, so the next part of the data wrangling process is dealing with missingness. All right, and we're going to be using the Hawkins test in the MIS-MEC package to identifying missing data patterns and also trying to figure out what mechanism, missing data mechanism, is actually explaining the missing data. When I think about missing data mechanisms, it's not the pattern. Okay, it is the process in which we are describing kind of what is the probability of those missing values and how they relate to the data itself. So one more time, it's all based on probability. And so there are 3 different types of missing data mechanism. There's MCAR, which is missing completely at random. There's MAR, which is missing at random, or there's MNAR, which is missing not at random. They're they sound very much alike, but they are so different. Oh, and the reason why I really like to focus on this is because we often hear within articles that folks are assuming MAR, so missing at random, because all of the most of the techniques for handling missing data assume MAR. Okay, so that's their underlying assumption. In reality, I do want you to know that in most cases, missing completely at random cannot be the actual reality, right? And sometimes even missing at random is not the true reality either of our data. And so this is why it is so important that we evaluate the mechanism and the patterns of our missing data. Okay, and so I am going to first be describing MAR, and MAR just suggests that the probability of our missing data within our variable X in this case is unrelated to X itself and could be related to any other variable that we have within our data set. So the missing data are related to some other variable under our investigation, but just not the variable itself where that missing value is. Okay. And so a more restrictive, the more restrictive mechanism would be MCAR, missing completely at random. And it suggests that the probability of missing a value on X is unrelated to any variable at all. Very fine distinction between MAR and MCAR, where we have no relationship between, or no probability of relating our missing value here to any variable, versus yes, we have the probability of missingness and it's related to some sort of variable, but beside itself, right? And so uh, this is when missing not at random comes into play, where it suggests that missing data are related to the variable itself or the scores themselves. One more time. I really love this type of figure. I really love figures to explain key concepts. In this case, we have this figure by Schaefer and Graham. This is like a quintessential article that we have here on missing data, or the art of missing data. And we can see through this figure that we have our missing data itself and the probability of that missing data, and it's not related to anything in the MCAR mechanism. However, that missing data can actually be related to some sort of variable besides the variable itself that missing data had come from. That's a MAR. And then M, MNAR suggests that missing data is related to the variable itself that missing data has come from. Okay. And so we are going to be using Hawkins test, and this Hawkins test is going to automatically group data by missing patterns. It's going to impute values and it's going to compare variances. And so we are going to be really focusing on our test statistic p-value here. And so if the p-value is greater than 0.05, then we fail to reject the null in that case, and that the missing values are missing completely at random. And if the p-value is less than 0.05, we reject the null hypothesis, and that the data are missing. We reject the null hypothesis that suggests that the data are missing completely at random. So another way to think about this is that the null suggests the data are missing MCAR, and the alternative would suggest that they are not missing using the MCAR mechanism. So one more time. If that p-value is greater than 0.05, then we would suggest that the null hypothesis is not rejected, in the sense that the null hypothesis suggests that the data are missing completely at random, versus the alternative that would suggest that MCAR, that the data are not MCAR, and that are something else. And so, or rely on a different mechanism to explain the missingness. And so all we have to do here is that we are in our markdown, we are going to generate a new R code chunk. So Option Command I for my Mac users. Okay. And so I am going to go ahead and leave myself a note that I'm going to be using the test MCAR normality normality function. I apologize about that. To test if missing data are missing, rely on the mechanism of missing completely at random. Okay. And so to go ahead and do this, all I have to do here is type out test and then M, and you will see that this function will automatically generate one more time, because I have already called in the package to use this function. So I'm going to go ahead and hit return. And then once I go ahead and hit return, I'm going to then tell R, hey, I want the following data frame to be evaluated. In this case, it's going to be T underscore DF underscore. Oh, and there it is already being generated. I can go ahead and hit return in this case. Another thing that I really like to do is I like to go ahead and assign this function to like the output or the results to an object. So I'm going to go ahead and assign my results to an object and I'm going to name it mcard test. And how I go ahead and I do that is I'm going to hit option and then dash for my assignment shortcut. And then mcar test is going to be the object name that is going to go into my environment. And so another thing that I'm going to do is I'm going to put another set of parentheses around this whole entire function here. And the reason why I'm doing that is because it will go ahead and print. So one more time, adding a parentheses outside of a whole entire code like this will then print my object. Okay. And so one more time, either you can hit the play button in this case, or you can go ahead and hit command return to run that one line of code. Give it a hot second. It may take a while. Mine is taking a little bit of time. And so let's talk about my output here. One of the first things that I see, given the summaries, are rather the number of patterns that we have, and then also the total number of cases used in our analyses, which will give you the total number, the highest or the greatest number of participants and then or observations, and then also the patterns. In this case, we have two patterns here. The group one are folks who ended up having complete data across all of our variables, and that is 4,339 of our cases have that pattern there. And then the second pattern is missingness on experience, and it should be 228 participants. And what I really care about is that p-value that is going to be generated from the Hawkins test. And so I can go ahead and look at it and I notice that it is super tiny, so small, right? Very small. And then I would go ahead and I would have to suggest that we have to reject the null in this case and that the data are not missing completely at random. And so I love how this function actually kind of just reassures you that your conclusion is correct here. And so it suggests that provided that normality can be assumed, in this case, the hypothesis of MCAR is rejected at 0.05. Okay. And so I usually don't like to stop there. I like to go on and I like to know the proportion of actual missing because Hawkins output does not give you that. And so I'm simply going to be using the miss underscore var underscore summary function. And I am just going to type that out into our RMD file. Oh, excuse me. Let me get this back up. And I'm going to close that. In our RMD file, option command I, and then I'm going to type out miss underscore var underscore summary. Okay, that'll automatically populate. You can go ahead and hit return, or you can type it all out and hit return. And then I'm going to type in those parentheses our data frame name. And then it's going to automatically generate. So I'm just going to complete it off by hitting return. And then I'm going to do command return to run that line of code. And so what this function does is that it'll give me the number of missingness, the number of cases with missingnesses, which we also get with a Hawkins test. But I also really like to know the proportion, and I would report both of these values in any given manuscript or report. And so I just have a quick write up here. The results from the Hawkins test suggests that there are two patterns and that missingness is occurring on the number of years. Okay, and that our p-value is less than 0.05. Therefore, we would go ahead and we would reject the null, which suggests that missing data are completely missing at random. And then let's see, I would also report the approximate percentage of missingness. In this case, it would be 5%, okay, of teachers' recorded years of experience that are missing. We are still going to go ahead and engage in imputation, which is a missing data handling technique. In this case, we are going to assume MAR, so we're going to go ahead and pursue the imputation. Before we actually get into imputation, there are a couple of housekeeping things that we need to do. We need to go ahead and remove that first column that has all those IDs. And so all I need you to do in this case is please go ahead and copy that line of code by selecting the copy clipboard, and then you're just going to paste it into your RMD file by creating a new R code chunk and then pasting it. Okay. And then you can go ahead and run that R code chunk for the T to remove that column 1. And so you are going to type out, if you would like to, T underscore DF underscore missing, and then brackets, followed by a minus sign, followed by a 1, suggesting that you want to delete column 1. Delete column 1 in the data frame. And then you are going to then assign it back to the data frame. Okay. So that way it actually happens. All right. And so now I have 3 variables in that data frame. All right. And in the next line of code, what is happening? Let me explain this to you. We are using the mice function to go ahead and impute. So multiple imputation, meaning we are imputing multiple times. And so this is where the M comes from. How many times are we actually imputing? Well, 50 times, because that is kind of like a baseline or a gold standard. And then we are going to go ahead and use a specific method. In this case, we're going to be using the predictive mean matching, which has been gone over in previous lectures. And then we always have to put a seed. Seeds are used for reproducibility purposes. Given that, for instance, if someone else would run this code, they should be able to end up with the exact same imputed data. If, for instance, you just decide that you want to go ahead and change that seed, your imputations are going to look different from mine, and your results would look different from mine. You can go ahead and try it, test it. It may be fun. All right. And so by you running this line of code, you're actually going to get imputed data. Okay. All right. And there are all my imputations. All right. I also want to quickly note that we went ahead and we assigned all those imputations into the imputed teacher data object, and we can open that object if we really wanted to. And you can see that it is a list of many of things, including our data, okay, including the data itself. All right. And so we can start making our way into talking a little bit more about the 3-step process that we are going to use to evaluate the relationship between our teacher callouts along with their class sizes and years of experience. So let's get started into that. All right, so let's get into the 3-step process that we are going to be using with linear models and their residuals. One of the first things that you should do when you are implementing a partial correlation in this approach or in this type of technique is that you want to go ahead and standardize your data. The reason why is because we already know that correlations are simply standardized, right? There's a standardized approach to evaluating relationships, and that regression itself is not standardized. So if we go ahead and standardize our data here using this regression, we would then end up with those standardized correlations, right? All right. And so then step 1, we need to go ahead and relate the outcome with the explanatory variable. One more time, we need to go ahead and relate the outcome with the explanatory variable. In this case, when I'm talking about the explanatory variable, I'm talking about the extraneous variable. Okay, I'm talking about the extraneous variable. And after you go ahead and relate these two things to one another, you're going to then pull the residuals. In the second model, you are going to go ahead and run a linear model again. And this time, you are going to predict the mean explanatory variable from that second extraneous or second explanatory variable. You're then going to go ahead and pull the residuals. Okay. Then you are going to relate the residuals that are left over. In this case, the residuals related to class size and to call out after controlling for that third extraneous variable, that third explanatory variable, teachers' years of experience. And so all of these steps here that I have listed out from 1 to 3 are going to be seen down below when we're actually dealing with our 50 imputed data sets. The code is going to look a little bit different because now we have to go ahead and implement a partial correlation for every single imputed data set that we went ahead and we created. In this case, one more time, M is equal to 50, right? We did that previously. And so the first thing that we are going to do is that we're going to actually use a function to make our life a lot easier. Because can you imagine writing out this code 50 different times trying to run a partial correlation on every single imputed data set? That would take forever. So we're going to go ahead and use the lapply function. And we're going to suggest that we want to pull and use 1 through the number imputed data sets given by M here. Okay, 1 through the number of imputed data sets, which is M. And then we're creating a function I. So these 50 data sets are going to go through the following function I. I is described by pulling only the complete data. One more time, pulling only the complete data from the imputed teacher data set. And I'm just going to show you why I have this line of code here. It's because within the imputed teacher data set, we have way more information than just the completed data itself, right? And so we only need to pull out the data. All right. And so then from there, we are going to scale the data just as I noted up above. We're going to standardize it, and we can go ahead and standardize it by using the scale function. So scale function. Let's go through this line of code. Mutate. We're going to some way, somehow change the 50 data sets. And this is why we're using the function mutate that is in, that I believe is in dplyr or tidyverse. And then you want to go ahead and use the function across. So I'm changing across all 50 data sets, and I'm going to change within these data sets the following variables. And this is why I use the concatenate or the C function or the C argument. I want to only pull out call out, class size, and experience. These are the only ones that I want to mutate across my 50 different data sets. And I want them to make sure that they're all numeric and that they all can be scaled. And that's what these lines of code are giving to me here. And then I do assign this new data into a new object, and that's going to be impute underscore std underscore t df, just so I know exactly that I have manipulated my original data set and I have named it something different now that I've manipulated it. Okay. I always do this. It's one of the things that it's just really good for reproducibility purposes. All right. And then we are going to then engage in the three-step process now. And so one more time, I have already only called in the complete data and I have scaled, meaning I have standardized that data. And now I'm going to be running a linear model on all 50 data sets here, where I go ahead and I am having my experience is predicting call out. So step one, where my extraneous variable is predicting call out, which is my outcome. That's step one. Step 1.2 is then just to collect all of those residuals, which I go ahead and I do, given that I have assigned this linear model to model co for call out. And so I pull those residuals using the residual function here, RESID, and in those parentheses, model co. And then I go ahead and I assign that to my residuals. So my res underscore co. I'm going to need those later on when I'm relating my residuals to one another. In step two, I'm running another linear model again. And in this time, I am predicting class size from that experience. I do want you to know that my data is the imputed data standard T for teacher, and then the data frame. And then I am assigning that linear model to model underscore SC for class size. Second step of step two is to go ahead and collect those residuals. And I am going to use the resid for residuals function. In my parentheses here, I have model CS, right? Just as up above as I have assigned. And I have assigned those residuals to res underscore CS because one more time, I'm going to need them so that way I can relate and create my or calculate my partial correlation. Step four, this is something that I didn't mention up above. And this is particularly for dealing with imputed data sets. You wouldn't do this if your data are complete. Okay. And so what I am doing here is I'm actually starting what is also known as a Fisher transformation to go ahead and pull all together all 50 data set partial correlations to get an average, right? Because we have to have one value, not 50 different values of partial correlations. We need one value, one partial correlation value. So what we end up doing here is unlisting. So meaning that we are pulling apart all of the data, and for each data set, we want to go ahead and we want to find a z value, and I use the aton function here. Excuse me. And then for step five, we have to find the means of those z values that we had just created in step four. And so we need to average, just as I said before. And so we grab the average. And so we grab the average by implementing the mean function, and then the z vals, which we went ahead and created up above. And then we assign it to z bar. Bar is usually for like x bar, which is another term for the mean. So z bar. And then in step six, which is unique just to this imputed data set or the imputed approach, is that we are going to find the variance within the partial correlations and between the partial correlations and the total variance across all imputed data sets. Okay. Let me see if I can fix this. All right. And so how we can go ahead and we find the variance within, we're simply going to be taking our Z evals, our Z scores, and we're going to be subtracting them by the mean of our Z scores. That will give us W. That stands within imputation variance. Now, between imputation variance is simply just the variance of those Z values that we went ahead and we created earlier. And then we're going to take the total. We're also going to calculate the total where we take the where we find the within imputation variance and we go ahead and we add it to 1 plus the proportion 1 over the imputed number or the number of imputed data sets, which is 50 in this case. And then we multiply that by the between imputations to get the total variance. And then from there, we can go ahead and calculate the standard error. Okay. Whew. It's a lot. There are a lot more steps to generating partial correlations when you have imputed data. And so I just want you to know one more time that this is not the case if your data are complete. So try to get complete data or figure out another way to deal with that missingness because there are other modern missing data handling approaches that are very, very, very popular. And so then step 7 would then be converting these like the Z bar or the mean back into correlations themselves. And then that's when we go ahead and we can get um, a pulled partial correlation. And that's exactly what we do with the TON. And then within TON parentheses here, we have Z bar and we're assigning that value to pulled R. And then in step 8, we actually end up calculating confidence intervals because this is what we would get normally if we were doing a partial correlation on complete data also. And so then and we can go ahead and use TON again. We're going to subtract 1.96 from Z bar and multiplying by the standard error that we have calculated up above using square root and then T var to get that SC. And we are going to, that will be the lower bound. And to get the upper bound of our confidence interval, we would go ahead and simply add 1.96. Okay. And so then we can go ahead and we can then print out all this information that we end up getting from this code. Now, all you have to technically do is you can simply copy all of this code using the clipboard. And then I'm going to paste that line or those lines of code rather into a new R code chunk. I'm going to go ahead and Command V for my preference. And then I'm just going to simply run all these lines of code that I have just gone over. And so then what you get is you get your estimate, which is going to be absolutely significant there, and the upper and the lower bound. And so it's suggesting that your partial correlation is significant. Okay, your partial correlation is significant. I do want you to know later on in the code, or in the HTML file, I actually have extra code. And this extra code is just to simply run a partial correlation with complete data and not having to do steps. I think it's like steps 4 through 8 because you have complete data and you just run a couple lines of code. So you can also see that this estimate that we have just calculated is very similar to the estimate we get down below when we have the complete data. All right, so let's go through a brief write-up. A partial correlation analysis was conducted to examine the relationship between teacher call-outs and class size while controlling for years of experience. After controlling for years of experience, the partial correlation was positive, strong, and statistically significant, following such that 0 was not included within our confidence intervals there. This suggests that even when a teacher has years of experience, the total of class size is significant related to the number of callouts. All right, now let's transition into semi-partial correlations. They are, meaning partial correlations and semi-partial correlations are very similar in the sense that we are going to be considering the influence of that extraneous variable. But in this case, it's going to be only on one variable. So that is, we're going to remove the influence of the third variable. And so we are going to end up getting, with semi-partial correlations, the unique contribution of the explanatory variable related to the outcome. One more time, we're going to get the unique contribution of the explanatory variable, the main explanatory variable on the outcome. And we're going to be removing the influence of teachers' years from class size only. In other words, the number of callouts is explained by whatever variance is left in class size after controlling for the number of years a teacher has. And so our hypothesis is very similar to what the partial correlations hypotheses were. In this case, our null suggests that there is no relationship, that rather than the correlation or the semi-partial correlation is zero, and that the total number of students does not uniquely relate to or predict the number of teacher callouts, and that the alternative would be that the correlation does not equal zero, that the total number of students uniquely relates to the number of teacher callouts. Now, I do want you to note here that within these hypotheses, I am not actually saying the words controlling for in relation to the number of years of experience. And so then the technique that we are going to be end up using, very similar to the partial correlation approach, where we rely on a linear model and its residuals after, and then relating that residual that we have left with the outcome. Okay, so let's just go through these steps. I do want to note that you technically could simply run a linear model, and you could simply look at the t statistic for that particular explanatory variable in relation to the outcome, and you would just simply report that. But I want to one more time stress the steps that we have here, because it explains actually the mathematics, or what is happening under the hood when we go ahead and we simply put in an LM code. So, first step, we use a linear model to test the unique relationship or relation between the explanatory variable and that third extraneous variable. We're going to collect their residuals, okay? And then from there, we're going to use those residuals and relate it to the outcome, okay? All right. And so, how we can go ahead and do this, we are going to do this with complete data. Yes, I said it, complete data. We don't have to go through all those steps that we did before, where we had to by hand calculate the confidence interval, I had to show you the within and between variance, within and between variance of those imputed data sets. So just a little bit different. And so what I need you all to do is need you all to copy the code that I have provided for you, and we're going to go over it quickly and briefly. And so create that new code chunk in your R Markdown. So doing that here, and I'm going to paste all of it. All right. And so for the first line of code here, what I am doing is that I am calling in, or I am reading in, the complete teacher data.csv file, which is in that zip code, and I am assigning it to semi-teacher data. And you can go ahead and run this by highlighting and then hitting command returned. Okay, so one more time, I'm using the read_.csv function to read in the data that I had in that zip file, and assigning it to semi_teacher_data. Now, in this data set, I also have that really, really weird column that I had before. So let me show you. You should always look at your data also. So semi, and there is that weird column, the one column, which is simply participant ID. And the reason why I'm calling it weird is because ID didn't actually print as the variable name. And so I'm simply just going to remove column one because I'm not going to be using that ID for any of my next following steps. But I need to remind you that I need to specifically remove that ID because I don't want to scale the data with that column. Okay, so I am removing that line there by simply typing out semi underscore teacher data. And then I'm using brackets here for my data frame, and I'm subtracting column one. I am subtracting column one. I'm reassigning this new data frame back to its original name by using the assign function there, and then the same original name. Okay, so let me run this for you. And I'm just going to triple check that it's gone. And sure enough, yeah, column one is gone. And so now I want to go ahead and scale my data just like I did before up above for the partial correlation. And so I am using the scale function. Okay. And the scale function here within a parentheses, I have the data frame name, and it's semi underscore teacher underscore data. And I want to make sure that it ends up being a full data frame. And I'm going to one more time just assign over semi teacher data. You are more than welcome, and you technically should for reproducibility purposes. And whenever you change a data frame, you should rename it to something else, meaning add a one or add a two or add a three. So that way you know that you can go back if you have to and get the original data or the previous step data. Okay. I'm going to go ahead and run that. And so if I go ahead and I look at my semi teacher data now, it now is on the same scale. All my variables are on the same scale. Not crazy wild. All right. And so step one more time, I just want to stress that we're using the linear model function to test the unique relationship between the explanatory variable, in this case it's class size, and that third extraneous variable, leaving me with the residual left in class size, because that's what I need, okay? So I'm using the LM function, and within the LM function, class size regressed on experience, or experience is predicting class size. And then I am stating that the data is equal to the semi teacher data that I had just created and modified by using scale. I am assigning this LM or this linear model to model underscore CS because I need to extract those residuals in the next step. And that's exactly what I do. Okay, so let me run this real quick. And so I can look in my environment and I can see that model CS should be there. There it is. Is that it? Yep. Okay. And you can see that I have coefficients. Residuals is what I'm literally pulling out. I really like this little like shortcut here. You can select the residuals and you can see the residuals at the bottom, and you can go ahead and print them if you'd like to. So there's a way to print out each one of those little elements in the model CS that we have here. I'm actually going to not be printing, but assigning those residuals to res underscore CS because I need to use them for my correlations, for my semi-partial correlation rather. And so I'm going to do that. And then I'm going to use the core.test function. Okay, core.test. And so the core.test function is going to give me Pearson's product moment correlation information. And you're going to see that I'm going to get a T statistic. I'm going to get a P value. I'm going to get degrees of freedom and confidence intervals, right? And so using this function, I am first going to relate my call out, which is in my semi-teacher data set. And I use semi-teacher data, and then the $sign is what helps me specifically specify the variable that I want to go ahead and use. In this case, one more time, it's call out. I'm going to then separate call out with a comma from my residual. So my first element is going to be call out, and my second element is going to be the residuals in this argument here. And I am going to assign it to semi-core. Semi-core. Okay. Something that I did that I haven't shown you all yet is that I used a parenthesis around a whole entire assignment and function, a whole entire line of code. And what this does is that it actually prints out the code for me when I do it. Because if I would actually remove that last outstanding parenthesis there, I would simply just assign the findings to semi-core. And then I would have to return, type out semi underscore core to go ahead and print out that those findings rather. So this is kind of just like a cute little shortcut, which I prefer, like a print shortcut that I use often also. So along the way, I try to give you all my nuggets that I use or that I've collected along the way. So that way you can go ahead and add them into your own toolbox. That way you can use them later on. Just shortcuts that I often find just useful. Okay. And so we have on my HTML or within my HTML, we can see the output that you actually have received also. It looks a little bit different because of my formatting here. So we have a a statistic. And this T statistic is used in order to infer about the p-value, right? And so then we suggest we would report a t-value, and we report the degrees of freedom, and we would also report our p-value as well when we are writing up our semi-partial correlation. And so I also want to note that we are provided with confidence intervals, and then we are provided that correlation estimate. And so a write-up would be the following. To assessing unique contribution of class size to call-out behavior, a semi-partial correlation was computed, accounting for teachers' years of experience. The semi-partial correlation between class size and call-out behavior was 0.8 with the T. You want to report your T and your degrees of freedom, along with your p-value and your confidence interval. And this, I like to kind of conclude with something like this, indicating that class size explained approximately 64% of the variance in call-out behavior beyond the variance shared with teaching experience. And I think this is what is so unique to semi-partial correlations that you technically really don't get or can't explain with partial correlation. So one more time, this is something that is unique to semi-partial correlations that you typically don't get with partial correlations. And it's the unique contribution of that primary variable, of that primary explanatory variable, after accounting for the influence of that third extraneous variable. Okay. All right. And I do one more time want to note that I have left you with extra code here. You can run a partial correlation with no missing data. If in the future you ever have to do this, I have those steps for you. You can easily just kind of paste in your own data frame names and then modify those variables that you are using. And then you can also, let me try to get this to keep going. And then you can also go ahead and I have for you a semi-partial correlation with imputed data as well, if you need that in the future. I also have a couple of references on related to missing applied data and to that teacher burnout study that I went ahead and I used. All right, so that concludes our partial and semi-partial correlation section. I would triple check that you went ahead and saved that lab section, and then I will see you next time. Reach out if you have any questions. All right, bye.